So as I said previously, over the years, researchers presented a lot of tricks and enhancements to DQN that helps improve performance in some domains. We won't discuss most of those, but at this point you are able to simply Google it and find those papers and read about them. Read about it yourself and see if it might be relevant to your project, if you have a project that uses DQN. In any case, I would like to discuss one such improvement, a simple one that is usually beneficial, and it relates to an issue that we previously discussed, that is the maximization bias in Q learning. Again, it's very easy to implement. In many domains it provides significant improvements. In some domains not as much, but it never hurts performance. Okay, I never encounter a situation where it hurt performance, and it might help performance, right? And again, it's very easy to implement. I'll show it to you in a second. So this improvement is attempts to address the maximization bias. We discussed the maximization bias previously, specifically at lecture 5 on TD learning. In this, this presents an issue where the max operator in Q learning uses the same value both to select and to evaluate the action. The action in our next state, right? And this fact makes it more likely to select overestimated value, resulting in over-optimistic value estimates. And you're more than welcome to go back to lecture number 5, where we actually showed an example. We showed a running example where this, or a toy problem where this issue manifests. And if you remember, we also discussed a technique to address this. We said we can address it with something called double Q learning. And we can actually use a very similar technique to enhance DQN, a very similar technique to double Q learning, which helps a lot in practice with the maximization bias. Okay, so the double Q learning enhancements that we previously saw simply trains two value functions and updates only one of the two value functions at each step, while considering the max operation from the other one. And this decorrelates the argmax operator from the max value, from the value of the argmax action. And we can do kind of something similar with DQN, and we can do it for free actually, without considering an extra approximator, because we already train in the vanilla DQN implementation, we already train 2 Q networks. So we just make use of that, and this is known as the Double Deep Q network algorithm, DDQN. We simply make use of the 2 available Q networks that we already train, right, for stability purposes in the basic DQN algorithm. And we use those to do double Q learning, right? So we simply change when we compute the target Q value, yj, where instead of considering the max Q value in the next state, we take the Q value for a next state that is chosen, right? So the Q value is computed using Q hat, and this is important, as we said previously, we have to keep that constant. But we choose the maximizing action not using the Q hat network, but using the other network, the Q network, the delayed network. And this is not precisely double Q learning as we saw previously. Previously we said that for double Q learning we need to train 2 Q estimations completely separately, and in this case Q and Q hat are not completely separate. Actually, every once in a while they're exactly the same, right? We set them to be exactly the same. But still, this helps a lot with denoising the maximization bias. Okay, so it's not a perfect solution, but it's a good enough solution that was evaluated in practice. I'll show you results in a second. And it actually was shown to help a lot in many domains. And here are some results. So this can be easily implemented in the basic DQN algorithm because we already have, right, in the basic algorithm, we already have two available Q networks, right? One is the Q and the other is the Q hat, the delayed, the one that is updated in delays. We have this trick, I mean, we use the two Q networks, as I said previously, in order to allow better stability in learning. This is an important trick that we use for a different purpose, but we can make use of these two Q networks for double Q learning, as we've seen previously. Right, and the trick is pretty simple. So now, instead of selecting, when we set the target value, the target Q value for each one of our sampled observations, sampled transitions, instead of taking the max Q value over all of the actions in the next state, we simply take the Q value as given by the delayed Q network. This is important for stability, as we said previously. But over the action, we choose the action from our other Q network. Okay, not from the delayed one, the one that we're constantly being updated, the one that we're constantly updating. So the other Q network is used to select the argmax, the action that maximizes the Q value, and the Q computation, the actual Q value, is retrieved from the delayed Q network, from the Q hat network, from the other one. Now you might say, this is not exactly the double Q learning that we've seen previously, where we had to separate between the two Q estimates. We said each transition trains only one Q estimate and not the other, and that's important for decorrelating our maximization bias, our Q estimations, for the maximal action. And this is true because, I mean, this is a real issue here. That is, these two Q networks are not completely independent of each other, right? Actually, every so often they are exactly the same. So it's not exactly Q learning, as I said before. We're losing some theoretical conditions here, but still, it keeps the same sample efficiency, right? In the original double Q learning, we said that the sample efficiency is halved because we can only use each one of the transitions to train one of the Q networks. So here we don't pay anything extra. We already have these two Q networks. However, we lose this independency requirement. And still in practice, I'll show you results in a second, and still in practice, it works pretty well. So, as I said, it doesn't cost you anything, and it just requires a small change in the code, and in many domains it's very beneficial. Let's look at some results. So here are some results again for different Atari domains. Here you see training curves, so the x-axis is the training steps in millions, so not the training episode, but how many steps have we interacted with the environment. While the y-axis for the top figures are the value estimations, okay, and you want to see that they are as close as possible to the true value, which is given in the orange line here, right? These results are just trying to show the bias and how the bias is addressed, right? So our estimations now becomes closer to the true estimation. While the bottom two plots are simply the training curves, right? The score over training steps. So we can see that both our estimation is less biased, right? When we observe directly the estimations. And also we can see how this is beneficial for the training curves, for training a better policy, at least in these two domains. right? And as I said previously, in some domains it's not really beneficial, but in none of the domains it was never shown to be counterproductive in any of the domains. Okay, some domains it helps, some not as much, but it never performs worse, at least in the domains that they report in the paper.